Hello, everyone. I am Sarah Moshtari, a PhD student at Rochester Institute of Technology. My talk is about a grounded theory-based approach to characterize software attack surface. My co-authors on this paper are Ahmed Okutan and my advisor, Dr. Mira Forli. Software security is becoming a day-to-day concern for organizations. Therefore, different security analysis techniques have been proposed to improve the security of software systems, such as vulnerability detection, software penetration testing, and the others. These approaches often directly or indirectly rely on critical parts of software, which are called attack surface components. Attack surface refers to the critical points on the boundary of software that attackers use to get into system, or critical parts of software that contain valuable content for attackers, and attackers try to cause an effect on or read data from them. Attack surface analysis is the process of identifying attack surface component and plays a key role in different software security analysis approaches, such as vulnerability detection and software testing. Most prior studies focused on security technique rather than identifying attack surface components. There are few studies that elaborate on the notion of attack surface. These studies define general concepts such as entry points, exit points as attack surface components, and then try to validate them as existing theories. These approaches focused on limited scope and example-based demonstration of attack surface. For example, they evaluated attack surface of an operating system or attack surface of web applications. Therefore, we lack a generic guidance to help security researchers in identifying attack surface components. The goal of this study is to propose a comprehensive attack surface model that can be used by researchers and security practitioners in different software security analysis approaches. We leverage a qualitative approach to identify attack surface components and propose the generic attack surface model. To reach the goal, we rely on publicly available vulnerability repositories and use an approach based on grounded theory. We use a Straussian grounded theory, which is a qualitative approach that extracts theories from unstructured data. It involves data collection and analysis, and theory is grounded on actual data. Vulnerability databases contain different unstructured data, such as natural language text that describes the vulnerability, or vulnerability patches and code samples. In this study, we leverage the Straussian grounded theory to identify high-level concepts which are related to attack surface components from this unstructured data that is available on online repositories. The Straussian grounded theory approach that we perform encompasses following activities. It started with defining topic, that is identifying attack surface component. Then we defined research question that led the rest of analysis. We performed different data collection and data analysis process that we call that coding. We performed data collection and coding process in different stages until we reached saturation. Saturation means reviewing more vulnerability data didn't provide new insights about attack surface components. Therefore, we sorted and categorized the defined concepts into higher level concepts and provided theories and taxonomies which are related to attack surface components. We defined research questions by inspiring from attack surfaces of a house. In a house, front door, back doors, windows are entry points, and there might be precious items in the house, such as safety box that attacker consider as target. And also there might be mechanism in building the house, such as emergency stairs that makes it vulnerable. Therefore, we define research questions based on entry points, target, and mechanism. The first research question is that where are the critical entry points in software system that are used by attackers to get in? The second research question is that what assets or components in a software system are targeted by attackers? And the third research question is that how do attack surface emerge and what types of mechanisms are utilized to reach the targets? For data collection, we use theoretical sampling. Theoretical sampling is a data collection process that is based on concepts derived from data. In theoretical sampling, all data are not collected at the beginning, and data collection and analysis is a circular process. We obtain vulnerability information from two publicly available repositories, which are common vulnerabilities and exposure and common weakness enumeration. We collected vulnerability report information from CVE MITRE list and NVD database. For each CVE, we collected CVE ID description, and also we considered references in CVE website to collect more information regarding vulnerabilities, such as information in advisories, exploit information, and also related CWE. And we use the MITRE CWE list to collect information regarding CWEs. We perform data collection in 3 stages. In the first stage, we randomly selected 500 CVEs from 2016 to 2020. After doing analysis in this stage, we found that the selected CVEs covered only limited number of CWE IDs, and some areas such as SQL injection and buffer overflow were theoretically saturated. Therefore, in the second stage, we randomly selected 200 more CVEs and used CWE as another resource for collecting data, and we collected information about 634 CWEs from introduced during design and introduced during implementation views in CWE. After doing analysis in the second stage, we found that some emerged concepts seem incomplete and there is no enough information regarding them. Therefore, in the third stage, we performed keyword search selection and selected 110 CVEs. We totally gathered information about 810 CVEs and 634 CWEs. In the initial stages of the Strassian grounded theory, we perform open coding. This figure shows the data we collected for ICSE2022-7248. As you see here, we collected different information such as CVE description and information that was available in security advisory and code repositories, and also information regarding their related CWE. During the open coding process, we highlighted the key points that are related to attack surface component by analyzing the collected data, and then we assign code to the key points. Code is a phrase that summarizes the information in the key points in a descriptive way. Here you can see the codes that we defined for entry points, targets, and mechanism related to this CVE. For example, service request, OBS command, and binary, blob, and JSON as input data were codes related to entry points. A stack memory or memory copy statement were codes related to target, and serialization, deserialization, and JSON serialization were codes related to mechanism. Throughout all process of the grounded theory, we perform constant comparison and memo-writing. We compare the existing concepts and categories with the vulnerability data to evolve them. And we used some nodes and mind map diagrams to identify relationship between concepts and define our preliminary ideas. In the intermediate stages of the grounded theory, we perform actual coding. During actual coding, we identify relationship between concepts and categorize them into higher level concepts. This figure shows the code that we defined for these two CVEs related to target. We had write to memory and copy memory statement as codes that we categorize them into higher level concept, which is memory manipulation. And we categorize array access and memory manipulation into higher level concept, which is application code. We also had heap and stack as codes that we categorize them into memory, and we categorize the memory into higher level concept, which is application resource. In last stage of the grounded theory, we perform selective coding. During selective coding, we sort the defined concepts and define the general and the final categories related to attack surface components. For example, in the selective coding process, we found that the codes and concepts that we define for entry points, targets, and mechanisms can be categorized into 4 major categories, which are code and program, which is an executable version of the code, and some of the concepts are related to system and network as environment that application runs on. All the steps of the grounded theory process were performed by all the authors of this study that have different software development and security experiences. The study was performed over 1 year, and all data is available on a public repository. This figure shows the categorization that we provided for entry point as a result of the Strassi and grounded theory analysis to answer the first research question. The concepts related to entry points are categorized into 4 categories, which are code, program, system, and network. At code level, entry points can be in user interface, such as input box or file upload, or they can be in other layers of program, such as input methods and handlers, or sometimes configuration file plays the role of entry point. And at program level, entry points can be related to design phase of the program, such as plugin components, chatting components that we consider in design phase, or they can be related to maintenance and deployment phase of the program, such as updating. And sometimes they are direct input that are sent to the program, such as command line arguments, and they can be indirect inputs that are read by programs, such as environment variable. And at system level, connection requests, service requests, loading drivers, and the others can be entry point. And at network level, packet, port, protocol, and the others can be entry points. We also provided the same categorization to answer the second research question for targets. For targets, components and concepts are categorized into 4 level categories, which are code, program, system, and network. Here you can see part of code level target components, validator, and HTML and web scripts can be target of attack in user interface, handlers, operating system command, database command, memory manipulation statements, and other kinds of program code statements, such as serialization, deserialization, file manipulation. Exit points can be target of attack at code level. At program level, we categorize them into program resource and program data. Any memory that is allocated for the program, such as stack memory, cache memory, shared memory, can be target of attack. We define program data from 2 perspectives. The first one is the location where data is saved, such as database. And the second one is the type of sensitive information that is available in data, such as database credentials. At system level, targets are categorized into operating system and firmware categories. For example, in an operating system, any action that affects the availability of operating system data, such as file systems, a specific file, and also service or servers that are running on an operating system can be target of attacks. And at network level, packet, network device, and socket buffer can be target of attack. We provided the same categorization for mechanisms based on code, program, system, and network to answer the third research question. Any mechanism that is used during software development, such as mechanisms used in user interface or other layers of program, or mechanisms that use to configure development framework, can make the system vulnerable. At system level, installing dangerous service or dangerous program can help the attacker to reach the targets. And at program level, any design decisions such as interacting with other servers or any action during deployment, such as enabling dangerous features, can make the system vulnerable and lead to emergence of attack surface component. And at network level, accessible network and using unsafe channel or protocol can make the system vulnerable. We conducted a systematic literature review by manual search of 5 resources to evaluate to what extent our results are supported by the literature. This figure shows the comparison result. The concepts in the figure are the concepts that are defined in our categorization, and the highlighted one are concepts that are covered by the literature. And the comparison results show that our categorization and attack surface model that we propose differs from the literature because it provides a comprehensive attack surface model at code, program, system, and network level. It also defines clear concepts. For example, in the literature, we have data item as attack surface component, but in our categorization, we clearly defines that data can be program data or system data, and define different concepts that are related to each category. Besides that, it provides a comprehensive code level attack surface component. For example, in the literature, we have input methods at code level as entry points, but we found that handlers or indirect entries also can be part of attack surface. We also perform a quantitative comparison to evaluate our attack surface model. The last column of the table shows the percentage of the concepts that are covered by the literature. The literature at code level only covers 10, 3.4, and 10% of entry points, targets, and mechanisms. And also on average, the literature covers 6.7% of code level concepts. Besides that, the literature in the best case covers 50% of network level mechanisms. And both the comparison results show that the proposed attack surface model covers previously introduced attack surface components, and it introduces 254 new components that didn't exist in the literature. In summary, in this study, we developed a comprehensive attack surface model based on entry points, targets, and mechanisms. The proposed model covers all the concepts defined in the literature, and prior works only covers a small percentage of the proposed attack surface concepts, and the model introduces 254 new concepts related to attack surface components. The proposed model can be used by researchers and security practitioners in different security analysis approaches. For example, developers can use the model during secure coding to identify critical parts of software which are related to entry points or targets. And also testers can use the model to prioritize their testing activities. Thank you for your attention. And if you have any questions, you can contact me.